to be here at the workshop. I apologize, the writing is a little bit small, and it's too late for me to make it bigger, so please do come forward if you have trouble seeing it. So as I imagine most of you know, there was interesting recent work by these authors, Pennington, Almhiri, Engelhardt, Marolf, Maxfield, Mahajan, Maldacena, and Zhao, about deriving the page curve for the Hawking radiation of an evaporating black hole using essentially souped up Ryutaki-Yanagi formula, using bulk holographic entanglement entropy formulas. And it seems like these results suggest that the gravity theory, the gravity path integral, knows more than we were giving it credit for. It knows about the page curve of the Hawking radiation. So with, in a recent paper with Jeff Pennington, Steve Schenker, and Zhenbin Yang, we were trying to understand this computation in more detail, try to understand how the gravity path integral knows about this, what it knows, what it doesn't know. And to summarize our paper briefly, the prescription, the holographic entanglement entropy prescription of these authors can be derived from the gravitational path integral using replicas, using the replica trick. In fact, in a way similar to previous work by Lukowitz, Maldacena, Dong, Lukowitz, Rangamani, and Dong and Lukowitz, the sort of novel aspect of this is that the replica geometries involve wormholes, Euclidean wormholes, or complexified Euclidean wormholes between the different replicas. And those wormholes allow you to compute the page curve, allow you to reconstruct the interior of the black hole, but they come with some baggage. Euclidean wormholes come with some conceptual baggage, and we don't understand the correct interpretation of that baggage. But I want to try to explain to you what we know. So I'm going to discuss basically section 2 of our paper. In the next session, Jeff will discuss section 3. So most of what I talk about is going to be based on this very simple model of JT gravity plus end-of-the-world brains with internal state index. So the action, it's a two-dimensional gravity theory, and the action is the JT gravity action plus a tension or mass parameter mu times the world line length of the end-of-the-world brane. So the end-of-the-world brane is just that. It's a place where space-time ends. And the classical solution for JT gravity with an end-of-the-world brane looks like this in Euclidean signature and Lorentzian signature. So at the left here, we have a piece of the hyperbolic disk with the standard asymptotic boundary of JT gravity, or rather a portion of that boundary shown in white. So that's like a constant radius surface in the hyperbolic disk. And then the other component of the boundary is the end-of-the-world brane. That's the red piece, and it follows a geodesic. Okay, so that's the Euclidean geometry. And notice that the end-of-the-world brane intersects the standard JT gravity boundary in 2 points. So in Lorentzian signature, the analytic continuation of this geometry looks like this. It was discussed in several places, maybe first in a paper by Korkulu and Maldacena. The end-of-the-world brane is behind the horizon. So we have a type of one-sided black hole with an end-of-the-world brane behind the horizon. Okay, so that's the gravity theory that we're going to be discussing for most of the talk. And to make it more interesting, we're going to assume that the end-of-the-world brane can have many internal states labeled by an index I. So it's going to be allowed to have k different possible internal states, and we're going to be interested in the case where k is very large. K is of order e to the black hole entropy, or even larger. So one way of motivating this type of model from the perspective of an evaporating black hole is that in this picture here, the end-of-the-world brane with many possible states is some kind of analog for the interior partners of the Hawking radiation. So if we have a black hole that's been evaporating for a while, some Hawking radiation has come out, and there are some interior partners inside that are entangled with the actual Hawking radiation. If there's a lot of Hawking radiation, then there are many possible states for those interior partners. And those are summarized in the different states of this end-of-the-world brane here. It's not supposed to be a precise mapping, it's supposed to be an analogy. Okay, so I'm just going to review the formula of these folks in the setting of this model. The discussion will be self-contained, so if you're not familiar with this work, then don't worry. But if you are, in case you are, I'll just explain how this model is related to that work. So in order to model the evaporating black hole, we're going to consider the following state of the total system. The state psi is an entangled superposition of k different terms, where we have state psi I with subscript b. B stands for black hole, so this is the state of the black hole. And it's a state of the black hole where the end-of-the-world brane is in state I. So there are k possibilities, and the sum runs over these k possibilities. And this other factor here in the state is a reference system, which plays the role of the early radiation in the evaporating black hole. So we have the early radiation here, which is entangled with the remaining black hole. And the total number of states is k. Okay, so what does the results of these folks, the so-called island conjecture or island formula, imply for this system? Well, let's try to compute the entanglement entropy in this state of the system R, the auxiliary system or early radiation. So we're supposed to, according to the rules of the island formula, we're supposed to consider two possible Ricciardi-Nagy surfaces, two possible extremal surfaces. One of them is the empty set surface, and for that, in that case, the entire contribution to the entropy comes from the bulk entropy, the entanglement between the brane and the auxiliary system R. There are k states, so the entropy is log k. The other possible surface is just the horizon of this black hole. In that case, there's an island shown green here behind the horizon, and the end-of-the-world brane is contained in the island. So for this surface, there's no bulk entanglement contribution from the entanglement between the brane and the radiation. The only contribution to the holographic computation of the entropy is from the, quote, area term at this point. In two-dimensional gravity, it's a dilaton term. In any case, it gives the entropy of the black hole. So if you didn't follow the details of that, that's okay. We'll explain it in the rest of the talk. But the island conjecture of these folks here would say that the entropy of the radiation in this state is the minimum of these two contributions. So it's the minimum of log k or the entropy of the black hole. And the transition between those two, as we increase k, is a model for the Page transition of an evaporating black hole. Okay, so what we're going to do in the rest of the talk is show how to derive basically this formula from the gravity path integral. Okay, so the first step is to compute the density matrix of the radiation. And if you start with this state here and trace out the black hole, you get this density matrix. So the matrix elements of the density matrix and the ij basis are these amplitudes here. These are just complex numbers. These are gravity amplitudes. And they're computations just in the black hole theory. And they're defined by the following boundary conditions. The boundary conditions are shown with this notation, which we're going to be using several times in the rest of the talk. So I want to try to explain it. The white line in the middle here is supposed to represent the asymptotic boundary of JT gravity, where we have the standard asymptotic ADS-CFT-like boundary conditions for JT gravity. So in some interval of Euclidean time here. So the length of this curve, or the renormalized length of this curve, should be proportional to beta, the inverse temperature of the black hole. So the boundary conditions are that we should have a boundary like this with renormalized length proportional to beta. and that the I and j indices here mean that we should have end-of-the-world branes that intersect the asymptotic boundary in 2 points here. The end-of-the-world branes should be of type I and type j. They should intersect at the 2 endpoints. Those are like these intersection points here where the end-of-the-world brane touches the asymptotic boundary. So those are the boundary conditions for computing this amplitude. And OK, so after we have the boundary conditions, we should try to fill them in with some gravity calculation and actually compute the number. And in this case, there's, well, subject to an approximation that I'll describe later, there's only one contribution which we can have, a topological class of contributions, which looks like this, where we fill in the boundary conditions with just this solution here, a piece of the hyperbolic disk. This is a saddle point of the gravity equations, but you can also do the path integral exactly in JT gravity because it's a very simple theory. The point that's important about this computation is that the same end-of-the-world brane connects to the j dotted index line and the I dotted index line. So that means that I has to be equal to j for this quantity to be non-zero. And we use the notation z1 for the path integral in this shaded region. This is some JT gravity computation for the integral over geometries in this shaded region. So the full answer for this amplitude, psi j inner product psi I, is this path integral z1 times Kronecker delta ij. OK, so after normalizing the states, by dividing by z1, we find that the density matrix rho r is just a maximally mixed density matrix, proportional to the identity matrix. And the entropy of such a density matrix is log of k, where k is the number of states. And another quantity that we'll discuss is the purity, trace of rho squared. That's equal to 1 over k. OK, so we computed the density matrix. We then computed the entropy, and we found log k. We only got one of these 2 terms. So what are we leaving out? How can we get the full island formula? OK, so in order to compute the entropy, we can use replicas. Use the replica trick and carry that out in the gravitational path integral. We'll discuss the von Neumann entropy later. That's harder to compute using replicas. So as a first step, we'll just compute the purity, trace of rho squared. So, all right, so we start with this formula for the state, and we just write down the answer for trace of rho squared. That's a sum of squares of these gravitational amplitudes. That thing we just get from that formula for rho r there, take the square, and then compute the trace. So what do the boundary conditions in gravity in this JT plus end-of-the-world branes model look like for this quantity here? Well, the important part of this quantity is the square of the gravitational amplitude. And the boundary conditions for that are shown here. We have 2 of these standard asymptotic boundaries of JT gravity. And they end in end-of-the-world branes of type I and j. And we have 2 copies of that. Here for one of the amplitudes, and the complex conjugate for the other amplitude. I should explain maybe I don't really know whether this notation is clear for the boundary conditions. Maybe one thing I can explain is the reason I'm drawing it with a wiggly line is that the boundary conditions in JT gravity constrain the renormalized length of the boundary, but they do not constrain its shape. So we have some arbitrary length, some fixed length but arbitrary shape here, and we need to fill this in with some 2-dimensional gravity. OK, so the main point of the talk, and it's a pretty trivial point if you, well, reduce it to this, is that there are 2 different geometries that can fill in these boundary conditions. One of them is just 2 copies of the previous calculation that we did. So we have 2 of these same things. This gives z1 times delta ij. So this contribution is represented here. That's z1 squared for the two factors. And we get 1 factor of k in the numerator, because when we sum over I and j are constrained to be equal, but we have 1 index loop, 1 red line index loop. So we get a factor of k. So this geometry here gives us k times z1 squared. And when we normalize the states to compute the density matrix, we have a k times z1 squared in the denominator. OK, so this is the sort of boring contribution. This is just 2 copies of what we had already. But there's another contribution you can have where the 2 asymptotic boundaries are connected by a type of wormhole, a Euclidean wormhole connecting the 2 sides. So there's only 1 connected geometry. The path integral on this space, this connected space, we'll call Z2. And an important point to notice is that here, when we sum over I and j, we'll contract these here and here. We're going to have 2 red index loops. So the contribution is proportional to k squared. So the numerator, we have k times z1 squared from this term, and then k squared z2 from this term. So as a result of this computation is 1 over k plus z2 divided by z1 squared. To try to understand this term, let's, for the moment, think about JT gravity in the crudest possible approximation, where we keep only the topological term in the action. So then JT gravity path integrals are proportional to e to the s naught times the Euler characteristic of the space. The Euler characteristic of the space for the computation of z1 is 1, it's disk-like, and the same for z2. So both z2 and z1 are proportional to e to the s naught. So this quantity here is proportional to e to the minus s naught. And obviously, you can do better than this crude analysis, but it's enough to make the point. So if k is not too big, then this term will be much bigger than that term, and we'll find that these disconnected geometries dominate, and we recover essentially this computation here. But if we make k extremely big, bigger than e to the s naught of the black hole, then this term will be bigger than that term, and the purity will saturate at a value that's independent of k. So that's a baby version of this transition in the von Neumann entropy between log k and s black hole. We have a transition between 1 over k and e to the minus s naught. And this transition is the basic effect that underlies the replica wormhole derivation of the island conjecture. OK. One point that I want to make is this sort of a parenthetical comment, is that we can get a little bit closer to the physical situation of an evaporating black hole by considering the following situation. We could have 2 black holes that are weakly coupled to each other, or 2 SYK theories that are weakly interacting with each other. And then we just let them interact with each other and equilibrate, and compute the entropy of one of the 2 systems as a function of time. If you do a Hawking-style calculation in the black hole context, you'll find that the entropy of one of the black holes grows linearly in time forever. So it's a huge violation of common sense. Similarly, if you do an SYK calculation and you keep only the naive replica diagonal saddle point, you'll find that the purity, it's harder in SYK to calculate the von Neumann entropy, but you can calculate the purity. You'll find that the purity decreases exponentially. So the Renyi 2 entropy is increasing linearly for time forever. But in the SYK context, you can find a replica non-diagonal saddle point where the two replicas are correlated with each other in a way sort of similar to this wormhole. And that thing gives a contribution to the purity that's independent of time. So it gives a floor value to the purity similar to this. For the case of the two evaporating, for the two interacting black holes, it's harder to do a calculation of to find the solution. It would be some complexified Euclidean wormhole. And we believe the solution exists. We have arguments that exist, but we didn't find it explicitly. Okay, so that parenthetical is over, and I'm going back to the simple model. Okay, so what I'd like to do now is try to understand how this result for the purity is consistent with our previous calculation of the density matrix. And this is where things start to get a little bit weird, where some of the baggage of the Euclidean wormholes becomes relevant. So this computation, we just computed the density matrix, and then we computed the entropy, and we found trace rho squared is 1 over k. Here, we computed the trace rho squared directly, and we found another contribution, 1 over k plus e to the minus s naught. The tension between these two different results can be traced to the following apparently contradictory answers that the gravity path integral gives for these amplitudes. So it says, the gravity path integral says that psi I inner product psi j is equal to delta ij after normalization. That's just this computation here. And it also says that the square of this quantity is equal to delta ij plus z2 over z1 squared. Those are just these two terms here. This one's proportional to delta ij. This one's proportional to, well, it's non-zero for any value of I and j. Now, these two statements are obviously literally incompatible with each other. So how are we supposed to interpret these? And one thing that you can notice is that, let's suppose, forget about gravity for a second, and let's just imagine that the right answer for this quantity was delta ij plus some small random term, rij, where these are some random numbers, times e to the minus s naught over 2. Let's imagine that this was actually the answer for psi I, psi j, and that what the gravity theory was computing was not literally this amplitude, but instead an ensemble average, where you average over these quantities rij in some ensemble with mean 0. When we take the average, this term drops out, and we get that. But when we take the average of the square, then this term here can be interpreted as the variance of this rij random variable. So it looks like, at least in this model, the gravity path integral is not literally computing quantum amplitudes. It's computing some kind of ensemble average of those amplitudes in some ensemble that's implicit in the gravity description. We didn't go out and try to describe a disorder average theory in this JT gravity plus brains model in the gravity path integral. We were led to that interpretation by trying to make sense of the results for the path integral. It looks like the path integral is implicitly computing some kind of a disorder average. Now, we don't have a proof of this, but we expect this fact to be also true of at least somewhat more complicated gravity theories like JT gravity coupled to bulk matter fields in a more standard evaporating black hole context. But, well, we're not 100% sure of that, but we believe it's the case. I'll come back to this comment a little bit at the end of the talk. Okay, so this was actually the main thing that I wanted to communicate, that so far we've discussed only the Renyi 2 entropy, or the purity. We found this wormhole contribution that give this behavior for the purity, which is an analog of the island formula. We tried to interpret it, and we were led to the conclusion that the gravity path integral was computing some kind of disorder average over these microscopic but erratic quantities. What I'm going to do in the rest of the talk is discuss, sort of redo this computation for the von Neumann entropy instead of the Renyi 2 entropy. This doesn't help us address the puzzling conceptual issues here, but it raises its own set of conceptual issues which can be addressed in an interesting way. Okay, so let's start trying to compute the von Neumann entropy. Using replicas, the way that you do that is you compute the trace of rho to the n, and then you analytically continue in n in some way, n close to 1. So the boundary conditions for trace of rho to the n are the following, using the same notation that we've been using so far. Here I have n equals 6. We have 6 of these standard JT gravity asymptotic boundaries connected by index contractions for the state of the end-of-the-world branes. The task in gravity is to fill this in all possible ways with gravity computations and then continue in n near n equals 1. So there's a family of geometries that can be continued in n easily. These are the replica symmetric geometries. And these are sort of at the extreme between completely disconnected geometries like the one on the left and completely connected n-boundary wormhole geometries like the one on the right. And if you go through the same steps we did before, you conclude that these two geometries, as a function of n, give the following contribution to trace rho to the n. We have 1 over k to the n minus 1 for this term. And we have zn divided by z1 to the n for this term, where zn means the path integral on a geometry like this with n asymptotic boundaries. So if you continue these near n equals 1, this contribution here gives log k. This contribution here gives the entropy of the black hole. I'm not explaining why, but this is a standard computation. So we get these two terms here that are supposed to appear in the island formula, but we don't know from this that we're supposed to take the minimum of them or add them together or I don't know what. And also there's all these things in the dots. Okay, so what we'd like to do is more systematically analyze the path integral in this, including the terms that are hidden in the dots. Okay, and to make the computation tractable, we're going to work in a type of planar approximation, where we take k much bigger than 1 and e to the s naught much bigger than 1, but with arbitrary ratio between k and e to the s naught. In this approximation, what it buys us is that the only types of geometries that we have to consider that fill in these boundary conditions are planar geometries like this. In particular, we don't need to consider handles in these geometries or crossings between the disk-like geometries connecting different asymptotic boundaries. Those things will be suppressed by powers of 1 over k squared or e to the minus 2 s naught. But even so, there's a rather complicated set of geometries that you have to sum up and somehow continue in n near n equals 1. And so we spent a little bit of time on the Wikipedia page for non-crossing partitions and free probability theory. And the next morning, Genbin had understood completely how this works. And he described it to us as, quote, fun. So I'm going to sketch it for you, and you can see if you agree with Genbin or not. So the fun begins by defining the resolvent of the density matrix rho r. So this is a matrix, has I and j indices. It's a generating function of all powers of the density matrix rho n. From this resolvent, we can recover the purities trace rho to the n for any integer n by doing a contour integral. So we do a contour integral around lambda equals infinity, and we take the trace of Rij, that's R with no indices, multiply it by lambda to the n, and do the contour integral around infinity. Okay, so now the method for computing the resolvent is a type of Feynman diagram summation trick for space-time geometries. I think this might have been the component that's supposed to be fun. So if we represent this Rij matrix with this notation here, then the boundary conditions for that thing are a rather weird set of boundary conditions. It's a sum of an infinite number of terms with a different number of asymptotic boundaries. There's a term with no boundary. That's the n equals 0 term here. Then there's a term with one asymptotic boundary, two asymptotic boundaries, and so on. And we need to fill these things in with all possible planar geometries. So this one can only be filled in with this geometry here. But the term with two asymptotic boundaries can be filled in with two different geometries. There's a disconnected one, and then there's the connected one that we've discussed already in the context of the purity. The case with three boundaries would have, I believe, 5 different terms that contribute. And we need to sum up all of them. To sum up all of them, you can write a type of Schwinger-Dyson equation where you say that this resolvent is equal to the Baire propagator here plus the following sequence of terms. And the way to think about these terms is the following. This guy here captures all terms where the first boundary that you meet is connected only to itself. This term here captures all terms where the first boundary that you meet is connected to one other boundary. There's a similar diagram that I didn't have room to draw where this thing is connected to two other boundaries. It would be a 3-boundary connected geometry with the resolvents in between. Now, JT gravity is simple enough, or actually dilaton gravity theories in general in an approximation are simple enough that you have very good control over these path integrals for these shapes here as a function of the number of boundaries. And actually they can be written as there's an integral representation for them inside of which the dependence on n is just some quantity to the nth power. That makes it possible to sum up all of these terms here as a geometric series. Okay. The result of that geometric series is the following equation now for the trace of the resolvent, R, the thing that we need in order to compute the purities. That equation is the following. You can see from the form of it that it involved some kind of a geometric series. The functions that appear here, rho of E and W of E, are simple explicit functions. Rho of E is the density of states in JT gravity, and W of E is a type of Boltzmann factor that has been modified by a term related to the brane. In the large mass limit of the brane, it's just a Boltzmann factor. Okay, so this is the equation that determines the resolvent. And well, I'm not sure if it looks easy or hard to solve, but it's sort of hard to solve. And Jeff took the lead on this, and he wrote an appendix to our paper with 15 pages where he showed how to solve this equation approximately in 7 different regimes that are necessary for computing the von Neumann entropy very accurately. So it's quite a fiddly thing, the correct analysis of this equation in different regimes. Alternatively, it can be solved numerically. So the main thing is that this is some concrete equation that can be solved to determine R as a function of lambda. Okay, so what do we do with that once we have R as a function of lambda? Well, we could plug that into this formula here and compute trace of rho to the n. But our goal in this whole discussion has been to compute the von Neumann entropy. So we need to continue in n, near n equals 1. And the integrand here is not analytic near infinity. So the lambda to the n factor has a branch point at infinity for non-integer n. So we're not going to be able to continue the expression written in this way. But what you can do, well, depending on how much time you've spent with resolvents, you'll know exactly what to do. But in that case, I'm explaining it in a sort of a roundabout way. But anyhow, if we think about the lambda plane, then the analytic structure of the resolvent is it has a cut along the positive lambda axis. So I'll call that interval C. And we can deform the contour of integration while n is still an integer, so that this thing here becomes an integral along the cut of d lambda over 2 pi I of the discontinuity of r across the cut times lambda to the n. And since the cut is along the positive real axis, we're far away from the branch points of lambda to the n. So this integral can be continued in n. So it can be continued in n, and in particular to compute the von Neumann entropy, you just put here lambda times log lambda. Okay, so if you take the expression that Jeff worked out in the appendix, approximate expression for r of lambda, and you do the integral, then you find the following as a function of log k. The entropy looks like this. It's linear. So the island conjecture, the island formula would be the following curve. It goes up and then across at log k equals s black hole. The actual solution to this equation is something that does the following. It follows this curve quite closely, and then it has a smoothed out transition over a width in log lambda that's of order 1 over square root of g Newton. So that's a type of smoothed out version of the page transition between the two forms that are predicted by the island formula. Okay. By the way, another way of thinking about it, which is helpful, is that the discontinuity of the resolvent across the real axis is just the eigenvalue density of the density matrix rho r. So this is directly the density of eigenvalues at the entanglement spectrum. Okay. I want to make two comments about this. The first comment is that the continuation in n is sort of conceptually non-trivial, because different Renyi entropies are sensitive to different parts of the thermal spectrum, and they experience page transitions at different values of k. And in particular, there's a range of values of k where all of the integer Renyi entropies have already had the transition. So the geometries that dominate those are all the maximally connected geometries, these wormhole geometries. But the von Neumann entropy is still dominated by effectively the disconnected geometry. So it's close to log k. And it would have been difficult to accurately compute the von Neumann entropy by starting from the integer Renyi entropies in that case, because they're all dominated by this other phase. But if you do the full summation of geometries, then of course you get the full answer. You get the correct answer for the von Neumann entropy. A second comment about this is that there are other contexts in holographic entropy computations where there are different surfaces that can dominate the entanglement entropy. And it would be nice to understand the transition between those more generally. The tool that we used here, which was inspired by free probability, does not appear to extend to the more general case. There's properties of this computation that are simple and that make it possible to use it. So it seems like an interesting open problem to try to find a principled way of doing the continuation in n for other types of holographic entanglement entropy transitions. Maybe some other tool is required, or maybe just a closer reading of the Wikipedia page for free probability. Okay, so let me try to summarize briefly. So we were motivated by this interesting work up there to try to understand how the gravity path integral implements the island formula, how to derive the island formula from gravity path integrals. And what we found is that the island formula, or this non-trivial quantum extremal surface, is secretly the n goes to 1 limit of replica wormholes. And a straightforward interpretation of those replica wormholes seems to lead to, well, it seemed easiest to interpret in the context where the gravity path integral was secretly computing some kind of implicit disorder average. That disorder average doesn't make a big difference to the von Neumann entropy, or the purity, because these quantities are self-averaging. If you, oh boy, basically the purity is a sum of a large number of, it's a sum of a large number of these terms. But in the ensemble, these individual terms have order 1 fluctuations. The sum of a large number of them is approximately self-averaging. But it seems that the interpretation of the wormholes requires, for this quantity, an interpretation in terms of some kind of ensemble. And there are other theories of gravity where, presumably, where you don't want such an interpretation. And understanding these is an open problem that Steve might comment a little bit on in the Simons meeting. Okay, thanks.